Today we are going to conclude unit 6, and in this we are our focus is on recognizing the connections between the solution to the collision problem and solution to the photoionization problem. And I mentioned that these solutions are connected to each other by the time reversal symmetry. So today we will establish these connections conclusively, and we need to understand what is meant by time reversal symmetry in quantum mechanics. So I will not get into too many details about it, but I will certainly explain what is meant by time reversal in quantum mechanics. It is quite different from what it is in classical mechanics, which we discussed in our previous class. Now, to begin with, we recognize that there is uncertainty between position and momentum, and this is the generalized position and the generalized momentum. So it can be anything, it does not have to be the physical x position and the physical linear momentum along the x direction. It can be any two canonically conjugate variables, which are generalized position and the momentum which is canonically conjugate to that. And in this sense, time and energy are also canonically conjugate. So they also qualify for this, but the uncertainty principle for energy and time, it has a very different basis than what it is for position and momentum. Although there is a certain similarity, so there is this delta q delta p business, and likewise there is a delta t delta e business, the uncertainty between energy and time. But the foundation of the uncertainty principle for energy and time is completely different from what it is for position and momentum. The reason is that there is really no operator for time in quantum mechanics. Time is just a parameter in quantum mechanics. Energy is a dynamical variable for which there is an operator. The operator for energy is the Hamiltonian operator, but there is no operator for time in quantum mechanics. Okay? So the foundation of the uncertainty principle for energy and time is quite different, and that is important in recognizing what is meant by the time reversal symmetry, because there is no operator for time. Now, it is just a variable, it is a parameter which changes continuously, it is not an eigenvalue of any operator, and that means that what is meant by time reversal has to be understood in its own context in quantum mechanics. This should correctly be called as motion reversal, as Wigner suggested, but it is often referred to as time reversal. It is a little bit of misleading terminology, but it is quite common. So everybody uses it and we are going to use it, but we are going to remember that what is actually implied is motion reversal is a more appropriate expression for what we are talking about than time reversal. This was introduced by Wigner in 1932, and time reversal is certainly not the inverse of time evolution. So that is the first thing we will spell out. So before we discuss what time reversal is, we will highlight what it is not. So it is not the inverse of the time evolution operator, and let me remind you what the time evolution operator does. So U is a time evolution operator. What it does is it operates on a state at time t0, and from this it gives you the state at a later time t. Okay? So this is the time evolution operator. It tells you how the system evolves from a time t0 to t. That is what is meant by time evolution. So now we will introduce time reversal or motion reversal, and this is what time evolution is, that if alpha is an arbitrary state, we operate on it by the time evolution operator, which is this 1 minus I h over h cross delta t. This is the usual time evolution operator in quantum mechanics that you have used to get the Schrodinger equation for the state vector, right. It is based on this essential idea which describes the time evolution of the state vector. And now we consider the time evolution of a time reverse state. So, you take an arbitrary state alpha, have a time reversal which is denoted by this operator theta. So, theta operating on alpha will give you the time reverse state of alpha, and on this you operate by the time evolution operator. So, there are two operators operating one after the other. So, what we expect is that if motion reversal is to mean what we expect it to mean, then theta operating on alpha will give you the time reverse state, and on the time reverse state, if you now operate by the time evolution operator, the result the result should give you the same state as you would get if you were to operate on alpha by the time evolution operator, but through a time interval minus delta t first, okay, and then reverse that state. Now, this is our expectation if motion reversal is to have a certain meaning in quantum mechanics. So, we demand what must be the properties of theta which will give us this particular description of the time evolution of a time reverse state, or the time reversal of a time evolution state which has been evolved backward in time. Okay. So, that is our question as to what properties of theta will give us a consistent description of this particular equivalence. Now, alpha being arbitrary, these two operators on the left side and on the right hand side must be exactly equal. Okay. So, this is the time evolution operator, this is the time reversal operator, and here these are written in the opposite order, but notice that this is plus delta t over here and this is minus delta t. Okay. So, it is not just the two operators which are written differently, one has plus delta t, the other has minus delta t. So, let us bring this to the top of the next slide, which is this, and now you multiply theta with 1. So, you get theta over here. From the second term you get I h delta t, this is h cross in the denominator and theta. So, everything is written in exactly the same order, and the same thing has been done on the right hand side. Okay. Do not tamper with the order in which theta and h appear, and do not tamper with the order also in which the square root of minus 1, the imaginary number I, is written. Okay. It is placed exactly where it is in the first equation. So, now cancel these two thetas, cancel these two minus signs. So, that gives you I h theta delta t equal to theta I h minus delta t, there is a minus sign over here, right. Now, get rid of the delta t's and you get I h theta equal to minus theta I h, and I could have cancelled I on both sides, but I have not done it deliberately. Okay. And that is what I had cautioned earlier, that do not tamper with the order of I. The reason of course is that you can pull out the I only if theta is a linear operator. Okay. So, this is the criterion of a linear operator. If theta were a linear operator, then theta I would be the same as I theta, because that is what a linear operator does. Okay. And then the right hand side would be minus I theta h, left hand side is plus I h theta, and this would give you h theta equal to minus theta h. Now, this result would be appropriate if and only if theta was a linear operator. We could accept it if this would give us consistent results, but does it? So, this is what we are led to by assuming that theta is a linear operator. Then let us take this result and operate by the operators on the left side and the right side on an arbitrary state which is an eigenstate of the Hamiltonian. So, H theta operating on an eigenstate of the Hamiltonian, let us say the nth eigenstate, would give you minus theta H operating on the same state, right. Now, En is an eigenstate of H, so it will give you En is the eigenvalue, and what it essentially gives you is En is a real number. So, you pull it out, and what it essentially gives you that theta En is also an eigenstate of Hamiltonian belonging to the eigenvalue minus En. We started with En as an eigenvalue, as an eigenstate of the Hamiltonian with eigenvalue En, and now we get the time reverse state also to be an eigenstate of the Hamiltonian, but with a negative energy eigenvalue. Now, would this make any sense? Consider a free particle, alpha is an arbitrary ket, so it should hold for any and every ket. Consider a particular case where your state is a free particle eigenstate, and how would you have a time reversed state belonging to an eigenvalue which is minus of En? What could that mean? It would be nonsense, right. A free particle has got only positive energy states, right. There are no negative energy states for a free particle. So, this would not make any sense. So, the conclusion is that theta cannot be a linear operator, because assuming that theta is a linear operator leads us to an inconsistency. So, now just to be careful, let us assume that theta is not linear, but it is antilinear. What it means is that when you write I to the left of theta, it would change its sign. Okay. Now, if you did that, then the right hand side would, I would change its sign, and then you will get I theta h, and the left hand side is I h theta. So, you get h theta equal to theta h, and now you get theta En time reverse state to be an eigenstate of the Hamiltonian belonging to the same eigenvalue, which is fine. Okay. So, there is no problem with this. So, our conclusion is that theta must be an anti-unitary operator. It cannot be a unitary operator, it cannot be a linear operator, it has to be an antilinear operator, and together with the preservation of norm it becomes an anti-unitary operator. So, the time reversal operator in quantum mechanics is an anti-unitary operator. So, t would go to minus t, but along with this minus I goes to plus I will go to minus I. So, there is a complex conjugation which is involved. Okay. So, t going to minus t and a complex conjugation are two immediate and essential factors which are involved in time reversal symmetry in quantum mechanics. They must go together, you cannot do just one. So, t going to minus t and complex conjugation, they go together in this anti-unitary description. These are the essential properties that an anti-unitary operator, if you have a theta to be an anti-unitary operator, and if it operates on two arbitrary states alpha and beta, giving you alpha tilde and beta tilde, then theta operating on a linear combination C1 alpha plus C2 beta will give you C1 star rather than C1. Okay. In a linear operator you would get just C1, but this is an antilinear. So, there is an antilinear property and another property connected with the norm. So, that together makes it an anti-unitary operator in quantum mechanics. It has got some interesting properties which I will not discuss at length, but mention them, that the time reversal operator would commute with the position operator, but it will anti-commute with the linear momentum, it will anti-commute with the angular momentum, but you can contrast this with the parity operator, which is again another discrete symmetry in quantum mechanics, and it has got some resemblance because it is one of the three discrete symmetry operations of the standard model. So, the parity, it anti-commutes with both the position and the momentum operator, but it commutes with the angular momentum, whereas the time reversal anti-commutes with the angular momentum, anti-commutes with the linear momentum, but commutes with the position operator. Okay. So, these are some of the differences of importance. And you can see how they relate to the Schrodinger equation, because if you write the usual Schrodinger equation, this is the time dependent Schrodinger equation. Now if you just let t go to minus t, then this argument t has gone to minus t, del over del t goes to minus of del over del t. So this is what you get from the left hand side. On the right hand side you have got t going to minus t. So this is what you get, and this equation that you get is certainly not like the Schrodinger equation, right. This is not the Schrodinger equation. But then if in this, from this you do a complex conjugation, every term you take a complex conjugation. So minus I will go to plus I, psi will go to psi star, okay. So let us do that. So minus I has gone to plus I, psi has gone to psi star, and now you get a relationship which is exactly the same as the Schrodinger equation, okay, and it is because t going to minus t and complex conjugation have gone together. So these are the essential characteristic features which are of importance in the boundary conditions that we are discussing, which connect the solution of the collision problem to the solution in the photoionization problem. So you will see how it is done, and I will illustrate it using a simple one dimensional problem first and then do the regular 3-dimensional problem, because there is a lot that one can learn through these one dimensional problems, these potential barrier problems, potential well problems that you do in your first course in quantum mechanics, and they are not just exercises in differential equation and solving boundary value problem. There is so much that one can learn from these one dimensional problem, and here is an example of this particular importance of the one dimensional problem, that if you have a one dimensional potential barrier of this kind, and you as always have 3 regions, region 1, region 2 and a region 3, and then the general solution you write in terms of the travelling waves e to the ikx and e to the minus ikx as a linear superposition of the travelling waves. You know which one is going to the left and which one is going to the right, and you know it because the time dependence is contained in e to the minus I omega t, and then depending on how the surface of constant phase propagates, that will decide which is moving to the left and which is moving to the right. So you have got in a collision experiment, now you must relate it to an actual physical experiment, because that is what quantum mechanics is about, that you are trying to describe a collision experiment, and this is a one dimensional collision. You have got an electron which is incident from the left, so e to the ikx is the one which is moving from left to right, okay, and that we know because the time dependence is e to the minus I omega t. So kx minus omega t is the phase, and constancy of that will require propagation of x from left to right. So you have got an electron incident from the left. What can happen to this electron now? It can get reflected and it can get transmitted, right. So you can get a reflection here B, and you can get a transmission here, which is this f e to the ikx. This is the wave in region 3 which is moving from left to right, and in region 3 you cannot have a wave which is going from right to left, right, because there is nothing in the problem which can send it back again. So essentially what this means is that this collision is described in which the electron is incident from the left, an entrance channel is unique. This is what I have been emphasizing, that the entrance channel is unique in this, then G must be 0, and G equal to 0 is the boundary condition which describes the collision in which the incident electron is incident from the left, okay. Now in photoionization you have an atom, you do not have a free electron in the initial state at all. This atom absorbs electromagnetic radiation, and as a result of this absorption the electron gets unbound. The bound electron, like 1s in hydrogen, if you give it more than 13.6 electron volt energy, it will become free, right, it will get ionized into the continuum. That is photoionization, and this electron escapes, and it can escape either to the left or to the right in this one dimensional problem, but only in one of the directions, because there is a unique direction for the exit channel. So, let us consider this unique direction to be the electron's escape to the left. So, this is the electron escape to the left, this blue line, blue arrow, which is escaping to the left. Now, where was this electron in the initial state? It was not there as a free electron at all. Okay, this is not a scattering experiment, it is only in the collision or scattering experiment that you had an electron in the initial state. So, in this case you can only simulate it by these dashed arrows. So, this is not the real electron, but coming in from both sides to cancel the flux. Okay. So, you sort of simulate, you pretend that it was there, that is the description, and this description would be appropriate to explain the photoionization process in which the electron escapes to the left. Now, what it essentially means is that the coefficient f in this case will be 0. So, G equal to 0 is the boundary condition for collision, f equal to 0 is the boundary condition for photoionization. In collision, the outgoing wave is in the final state, and in photoionization you have got ingoing waves in the initial state. Okay, so, that is the relationship, and what we are going to see is that these two states are connected to each other by the time reversal symmetry. Okay, you expect this, because if you were to run the film backward, that is the process you can imagine to be seen. So, this is the motion reversed state, and we will find that these are connected by the time reversal symmetry. So, if you operate on the collision process by the time reversal operator, you would get photoionization, and sometimes photoionization is referred to as half scattering or half collision. Okay, that is a very common term which people use essentially because of this particular connection. So, you have got outgoing waves in the final state, and this is the 3-dimensional picture that we expect to emerge. Remember these pictures because they are going to be important, they will come back in our discussion. When we conclude our discussion on the 1-dimensional problem, we will do the 3-dimensional problem also. So, if theta operates on this collision experiment, you would expect this photoionization process to be seen as a result of this operation. So, these are our boundary condition, G equal to 0 for collision and F equal to 0 for photoionization, in which the exit channel is unique. In collision it is the entrance channel which is unique, and the conditions are expressed by G equal to 0 and F equal to 0. Okay. Now, I am going to follow the treatment from Fano and Rao's book, which is a very nice book which explains these things nicely, and I have a quote here from this book: "The developing procedures that serve to implement alternative descriptions of a wave function for a realistic system is a major goal of this book, because you can express a wave function in any set of basis set, and which basis set is most appropriate in a given condition is a choice that you are free to make, and you make the best choice which will bring out the most physics. Like you can solve the problem of the planetary problem, the Kepler problem, if you like, in Cartesian coordinates, you can do it in parabolic coordinates, you can do it in spherical polar or any coordinate system, nothing wrong with it, but whichever is the most appropriate, whichever gives you the most insight in physics, right, that is the one that you choose. So, you would use plane polar coordinates for the 2-body Kepler problem, and it is a similar kind of situation over here, that here it is not just the simplicity of the equations, but what is the most physics that you can extract by making an appropriate choice of the basis. Mathematically they are all equivalent, but one gives you a deeper insight into the physics than the other, and that is the choice you have to make. So, here they propose alternative basis set, not just e to the ikx and e to the minus ikx, they can certainly be used mathematically, that is a complete basis, no problem, but you can use any other basis set like u plus and u minus with appropriate coefficients c plus and c minus, and you can see what kind of physics you get by making some alternative choices. So, here for region 1 they propose u plus and u minus to be given by these cosine functions, but with two different phase shifts. Okay, one has got a phase shift delta plus, the other has got delta minus. For region 3 you have similar u plus and u minus, okay. And then if you operate on u plus by the parity operator, you find that you get the solution u plus for region 3, whereas if you operate on u minus you get the negative of the solution for u minus. So, instead of travelling waves, you can use solutions which connect to the parity operator rather than the free particle Hamiltonian. So, you can use different kind of basis sets over here, and this particular choice is just for completeness. For region 2 also I have given the wave functions over here, but they do not appear very much in our discussion because you are going to see only what is happening in the asymptotic regions, which is where the electron gun is or which is where the detectors are, because that is what is most important to the experiment. So, now if you write these wave functions, earlier we had used this e to the ikx and b e to the minus ikx, corresponding functions over here, the coefficients are now given by these c plus e to the minus I delta plus, because if you just carry out those transformations between the basis sets, okay, you can write the same wave function in either basis, do the transformation, and this is what you get by doing a little bit of algebra which you can do at home. So, you get these coefficients. So, this coefficient takes place of A, this coefficient takes place of B if you were to rewrite these functions in terms of the travelling waves, okay. So, you write these functions for the region 1 and also for region 3 similarly. So, for region 3 these are the this is the linear superposition of e to the ikx and e to the minus ikx, but now the coefficients instead of A and B are now in terms of the c plus and c minus and the phase shifts. So, now we know that G equal to 0 is the collision experiment, right. F equal to 0 is the photoionization experiment. What essentially it means is that this box will be equal to 0 for collisions and this box will be equal to 0 for photoionization, and let us see how these are related to each other. So, let us write this out. So, this is the box which goes to 0 in the collision experiment. So, c plus e to the minus I delta plus is equal to minus of c minus e to the minus I delta minus. So, this is what you get for the ratio of the coefficient c plus to c minus. This is essentially one phase shift with reference to the other, right, it is the phase shift difference. So, you get this coefficient in terms of this difference for G equal to 0 for collision. What do you get for photoionization? Photoionization you get this relationship, let us write it over here. So, you get c plus upon c minus equal to minus e to the power plus I delta minus delta plus. Now, what is the connection between these two? They are complex conjugates of each other, okay, and this is exactly what we expected, and this connection becomes transparent by making this choice of the basis set, okay. That is the advantage in choosing this basis set. Now, while we are working with the one dimensional problem, I will mention a few other properties also which can be of importance. So, here I highlight this particular result, that the motion reversal that you expect to witness as you operate on the collision process by the time reversal operator, giving you the photoionization experiment, right. This relates to the complex conjugation and time reversal goes together, right. So, this is the essential message from this, which is why, as I mentioned, photoionization is sometimes called as half scattering. And while we are at this, I will mention a few other learnings from this one dimensional problem which are important in scattering theory. You have this region 1, 2 and 3, and you can apply the boundary conditions at minus A and plus A, you have the equation of continuity which is well known to you, right. So, this is the current density vector, and you can get the current density vector for the 3 regions, subject it to the equation of continuity, the divergence of J is equal to the negative rate of change of the probability density, right, that is which is just the statement of conservation of flux. And then for stationary state, since del rho by del t vanishes, the divergence must vanish, okay, and that is what gives you the connections between the coefficients A and B and C and D, and you also get similar connections between CD and FG. So, you can write it in a matrix form, right. So, A is some linear superposition of C and D, and B is some linear superposition of C and D, right. So, these are matrix equations, you just have 2 by 2 matrices. So, I am writing only the structure, you can get the actual reflection coefficient, transmission coefficient that you would have done, but then you can eliminate C and D from this and you will get A and B in terms of F and G. Now, these are of importance because these are the coefficients in the asymptotic regions, okay, and those are the ones that are of direct consequence to your source and detectors. Now, you can do something else by playing with these matrices. You can also write the coefficients B and F in terms of A and G by simply playing with these 2 by 2 matrices, right. It is just a matter of writing those equations, and instead of writing it in terms of the matrix M which I had defined in the previous slide, you write the coefficients B and F which are the coefficients of the outgoing waves, okay, in terms of the coefficients of the ingoing waves, okay. Now, this matrix which connects the coefficients of the ingoing waves to the coefficients of the outgoing waves, this is called as the S matrix, and in fact Heisenberg did a lot of work developing a formulation of quantum mechanics in terms of the S matrix formulation. This is the famous S matrix formulation of quantum mechanics by Heisenberg, and this is called as the scattering matrix or the S matrix. So, you can just set up these 2 by 2 matrices, and there is a lot that you can learn from this this problem, and you can write this equation for the transpose. You transpose both sides, so T corresponds to the transpose. You can transpose and complex conjugate, okay. So, this is very simple algebra. This is transposition and complex conjugation, and subject it to the equation of continuity. For stationary states, you will find that the divergence of J is 0, which means that dJ by dx is 0 in the one dimension to talk about. If you set up these equations, you find that the conservation of flux is expressed by this relationship A square plus G square, which is the flux of the ingoing waves is equal to the flux B square plus F square, which is the outgoing flux, okay. Now, if you see this, now since BF is written in terms of A and G through the scattering matrix, you construct this matrix multiplication. This is the complex conjugate and transpose of BF. This BF is written in terms of this S matrix. So, this is S operator, S matrix operating on this column matrix AG. B star F star is nothing but this, okay. What do you get from here? Now, this is A square plus G square on the left hand side, right, and essentially what you get is that the S matrix must be a unitary matrix, okay. So, the unitarity of the S matrix is connected to the conservation of flux over here, and these are some important properties in collision physics which become handy later on, but our immediate interest is on seeing the time reversal symmetry in this process, and we have already recognized that what we are going to have to do is to let T go to minus T and complex conjugation together. We have already seen it, how it plays out in the one dimensional problem, but the problem of interest to us is the 3 dimensional problem, in which you can always write the total wave function in terms of these. The radial part we know is the same thing as you get for a free particle, except for the phase shift which is caused by the target potential, right. So you have got a form which is exactly the same as the plane waves, with the difference that there is a phase shift which is a scattering phase shift delta L, okay, and these CLs are the arbitrary coefficients. Now what you would do is choose CL to be e to the I delta L. Now if you choose e to the I delta L, CL to be e to the I delta L, then what do you get? You get the total wave function, you put CL equal to I delta L, you are, or do not forget the scattered part, okay. So it is a sum of the plane incident wave and the scattered wave. So in the scattered wave it is only the outgoing part which is e to the I k r by r, which has got this phase shift 2 I delta L, okay, and this is your scattering solution for the choice CL equal to I delta L. So CL equal to e to the power I delta L is the boundary condition which gives you the correct solution for the collision problem. Now let us see how it connects with the time dependent process that we are really picturizing, because we know that the time dependence is contained in this e to the minus I omega t. So you multiply everything by e to the minus I omega t. So you have got a time dependent function. Now I have written a superscript plus here to denote that these are the outgoing wave boundary conditions corresponding to the collision experiment, okay. So here I have got e to the I k z minus omega t, it is coming from here, okay, and here I have got k r minus omega t. So this is the incident plane wave moving from left to right. This is your collision boundary condition, this is the outgoing wave boundary condition, right, and you get the picture that you expected to see. What has given you this picture? Just the way you had g equal to 0 over there, here the choice is C equal to e to the I delta L. Now let us rewrite the total wave function, okay. We begin at the beginning, we have an arbitrary solution for the scattering problem with arbitrary coefficient CL, but this time around, since we expect the complex conjugation to appear in the boundary condition, we have seen it in the one dimensional problem. So you make the choice CL equal to e to the minus I delta L. Now last time we did e to the plus I delta L. So now what does C equal to e to the minus delta L give you? So this is what is called as the ingoing wave boundary condition. This is denoted by a superscript minus over here. This is the e to the minus I delta L which takes place of the CL, and now you multiply every term by e to the minus I delta L. So this e to the minus delta L will kill this and it will give you a 2 delta L over here, right. So that is what you get a 2 delta L over here, this delta L is killed by this e to the minus delta L. This is the total wave function with ingoing wave boundary condition. Now what do you get? You have the incident plane wave which we have written earlier in this form already. This is the scattered part, because if you subtract this from the total you will get the scattered part, right. So all I have done is to subtract this from the total function, I subtract the plane wave, so I get the scattered part, and I write the total wave function as a sum of the incident plane wave and the scattered part. Now fair enough, this looks like the solution problem, but there are essential differences if you have noticed already, but they will become manifest in our discussion. This is our total wave function with the ingoing wave boundary condition with the choice Cl equal to minus I delta L. This is straight from Fano and Rao's book, this is from page 64 of their book, and now we will do the complex conjugation and the t going to minus t, okay, and see what picture we get. So you do a complex conjugation, so e to the ikz goes to e to the minus ikz, e to the minus ikr goes to e to the plus ikr, there is a minus sign here and a 1 over I here, so you get a 1 over I here but with a plus sign, okay, that is because of the complex conjugation, right. And this complex conjugation, from this minus sign you get a plus sign here, okay. So we have done the complex conjugation. This is the time dependent part, which is e to the minus I omega t as always. So you multiply it by e to the minus I omega t, you get this form, bring it to the top of the next slide as it is, and now you let t going to minus t, because you have already done complex conjugation. Now you let t go to minus t. Now what do you get? You get e to the, so this was plus omega t, this becomes minus omega t, this was minus omega t, this becomes plus omega t, that is what has happened, everything else remaining the same. And the picture that you get is, this is a plane wave which is moving from left to right, and this is kr plus omega t. Now what is that? That is a spherically ingoing wave, right, because the surface of constant phase will have kr plus omega t will be constant, and therefore dr by dt will be negative. So the radius must decrease, which means that you are talking about a spherical wave which is converging onto the center. But is this the picture that we were expecting? We were expecting this picture, right. Now there is a difference, and that difference is because there is a factor which some of you perhaps noticed and some who did not, that there is a minus sign here, okay. This is the minus sign which has cropped up in our analysis, and it is this minus sign which I am going to discuss, because you know that if you add pi to theta, cosine of theta plus pi gives you minus cos theta. So PL of minus cos theta becomes PL of cosine theta plus pi, right. And this is the big difference, because in collision it is the entrance channel which is unique. So all the angles are measured with respect to that direction. So if it is coming like this from left to right, all the angles are measured with respect to this, okay. In photoionization it is the exit channel which is unique. So all the angles are to be measured with respect to, there is only one direction with respect to which you can measure the angles, which is the direction of the exit channel, and that is going in the minus in the other direction. So z goes to minus z, and that is contained over here, that this PL of minus cos theta is PL of cosine theta plus pi. So there is a reversal of the z axis, and essentially what it means is that reversal of the z axis will change this z to minus z, and that will give you plus I kz plus omega t over here, and everything else remains the same, with this minus cos theta becoming cos theta now, but theta is measured with respect to the escape direction, and now you have the correct picture which is emerging, okay. So the solution to the photoionization problem comes straight from the solution to the collision problem through the time reversal symmetry. All you have to do is let t goes to minus t and have a complex conjugation effected simultaneously. Now this is absolutely important, and this is our main conclusion, that Cl equal to e to the I delta L describes the collision, which is the outgoing wave boundary condition. Cl equal to e to the minus I delta L describes photoionization, which is the ingoing wave boundary condition, and these two processes are related to each other through the time reversal symmetry, okay. And you have this picture that the time reversal operator which operates on the collision process gives you the time reversal process, which is photoionization. we have discussed this from the beginning of this unit, that they have got the same final states, but the initial states are different, and there is a certain symmetry which connects one to the other. So, the symmetry which relates them to each other is the time reversal symmetry, which involves t going to minus t and complex conjugation going together, and this is important because now you get the correct final state solution with the ingoing wave boundary condition, which will be this PL of minus cosine theta. So, this is the part that you get in the scattering solution. In the collision it is different, right. So, when you evaluate the matrix element for photoionization, that there is a certain transition from the initial state to the final state, and that matrix element, that probability amplitude is represented by this matrix element. Which wave function would you put in over here? It must be the wave function with ingoing wave boundary condition and not the outgoing wave boundary condition. You will not get correct results at all. Okay. So, you must make use of these ingoing wave boundary conditions in describing the photoionization experiment, and when in the next unit we will describe how in what directions the electrons go as a result of photoionization, what is the angular distribution. Okay, they do not necessarily go evenly in all the directions. So, when you discuss the angular distributions of the photoelectrons, you have to deal with this matrix element for transition from initial to the final state, and you must use the correct final state wave function. This is not, it is a plane wave, okay, it is a plane wave solution, but it is an appropriate solution with correct ingoing wave boundary conditions. So, this is what must be used, and we will be discussing this in our next unit. So, with this result we conclude our discussion on unit 6. The primary reference for this is Fano and Rao's book. You will also find things in Joshain's book and Wu and Umara. So, if there are any questions I will be happy to take, otherwise in the next class we will go over to unit 7, in which we will describe the photoionization cross section and angular distribution. We will also use results of time dependent perturbation theory, the Fermi's golden rule, and so on. So, you would have met some of these things in your earlier course in quantum mechanics, but we will go through them because we will require them in the process. Questions? Thank you.